Hi everyone. So today we're going to take a look at a technique that we can use to integrate by hand. And really it's a method of finding an antiderivative called U-Substitution. And I think you'll see once we get started why it's called that. But I want you to just recognize kind of the purpose. The reason that we're doing this is to reverse the chain rule. So let me do just a quick example with you of what I mean by that. So let's say, for example, I give you a function like y equals sine of 4x squared plus 3. And I say take the derivative of that, right? Well, hopefully you're looking at that and saying, I need the chain rule. So I need the derivative of 4x squared plus 3. That would be 8x. And then you would multiply that by the derivative of the sine, which is cosine. But then this inside part stays the same. That should be old news, right? This is stuff that we did first semester where we did the chain rule, okay? So now the idea is if I hand you this function and I say take an antiderivative, well, we don't have a product rule that we can use for antiderivatives. But if we recognize that this came from the chain rule, we may be able to reverse it, okay? And so what U-substitution does in general is it takes this thing, this 8x, and says, hey, don't really worry about that 8x. That just came from that inside derivative. And then it kind of takes this thing and just sets it aside, okay? And I'll explain what I mean by that in just a minute, so that all you have to focus on is this cosine. And then you can say, all right, well, the antiderivative of cosine is sine, and then you can kind of put this 4x squared plus 3 back where it goes, okay? So that's what U-substitution is trying to do. We have to be a little bit more formal about it. I mean, this one is probably pretty obvious that this came from chain rule, but they're not always so obvious. So that's why we need kind of a technique or a method, okay? So the way we're going to start with this one here, the sine of 3x, and we want to identify what we want u to be. U should always be, maybe not always, but most of the time, the best thing to choose for u is a function inside another function. So for example, here I see 3x inside of a sine function. So I'm going to say that u is equal to 3x. My next step then would be to take a derivative of u, not an antiderivative, but a derivative. And so I'm going to write that down here. I'm going to call it du dx because that's my notation for derivative, right? And the derivative of 3x is just 3. Now, we haven't really talked about this expression before. We've always just said, okay, that means derivative. But these are two separate quantities. This is how much u has changed, and this is how much x has changed. So this is change in u with regards to change in x, like rise over run, right? This dx is actually the same as this dx. Those are the same quantity. They're measuring the same thing. So what I want to do with this is I want to move this around and get dx by itself. You'll see why in just a second. Some of this you're going to have to just sort of follow what I'm doing, and then I promise at the end you'll see like why I'm taking the steps that I'm taking. So we're going to move the dx to the other side. Du equals 3dx. And then I want the dx alone, so I'm going to divide by 3. So this side is now 1/3 du equals dx. Now, you may be sitting there and you have no idea why I just did what I did. I'm going to show you why in just a minute. But stop here and make sure you understand algebraically how I got from here to here. Okay? And by the way, I usually skip over writing this step. I did it this time to explain it to you. But usually I just jump straight to this. I just jump straight to like, hey, I took the derivative, so I'm going to put a dx on that side. And then swing it over to this side so that dx is by itself. So here's what we want to do now. And this step is important. This is a step that people sometimes skip and then they get lost in their own work. We want to rewrite this integral using our U-substitution. So I'm going to write this as an integral of sine But then instead of 3x, I'm plugging in u. And then the problem we run into here is, let me just write this down for a second. If I put a dx there, this is telling me to integrate with respect to x, but my function is now a u value. So when these variables don't match, I can't actually take an integral. That's why we did what we did here. Because now I can say, I'm just going to replace that dx with a 1/3 du. So really rewriting this integral should look like this. Sine of u times 1/3 du. And then this 1/3 is a constant multiple, so that can actually move out in front of my integral. So I can say this is now 1/3 integral of sine u du. And the important thing is that this variable matches this variable. And the reason that's important is because now I need to take an antiderivative. Don't forget that that was our whole goal, right? The whole reason we're doing all of this is because this told us to take an antiderivative. And I've rewritten this thing a bunch of times, but I haven't actually done that. By the way, you probably don't need to rewrite it that many times. You're going to get better at this where you can kind of combine some of those steps. But again, with this first one, I just want you to see every little thing that I'm doing. Okay, so now I need an antiderivative. My antiderivative keeps the 1/3. And then I'm going to say the antiderivative of sine is negative cosine u. This would technically have a plus c, but I'm going to add that in the next step. And then the last little thing I want to do is swap this back out for x. So remember this, that u is equal to 3x. This u is like a placeholder. We kind of just put it in place of 3x, so I didn't have to deal with that mess. So I'm going to turn the u back into a 3x and make this negative 1/3 cosine of 3x. And then I'm going to add on my plus c because it's an antiderivative. That's the U-substitution process, okay? And so what we did is we kind of took this 3x, we set it aside. We made it possible to integrate this function that was left by swapping this out for a du, and then we actually took the antiderivative. So I want you to notice I did this in 3 different colors because your work sort of goes in 3 phases. The first phase is find u and take a derivative. The second phase is rewrite your integral, simplify it, clean it up however you need to. And then the third phase is take the antiderivative and swap your u back out. Okay? Now, this is actually a problem that when we first learned how to do antiderivatives, I talked to you about, hey, when you see this 3x, all that means is a 1/3 is going to show up in your antiderivative. This is one that you probably could have done without U-substitution if you were good at that trick. And I want you to be good at that trick. Okay? I just chose this one to start with because it was pretty easy as far as U-substitution goes. But I would hope that you wouldn't need U-sub for this. There are some problems later on the page where you'll definitely need U-substitution. So I would suggest you start the next one without me. Pause the video, start it, see how far you can get, and then pick the video back up. I will go ahead and go through it, but this would be a good place to see how far you can fly solo. We have to pick our u, right? So I'm picking the function that's inside another function. So I see a 4x minus 1. So u is 4x minus 1. I'm going to try to model more of like how I would actually write these out every time. So then I'm going to take a derivative. Du, well, my derivative of 4x minus 1 is just 4. And then this side gets the dx. And that means if I move the 4 to the other side, I get a 1/4 du equals dx. Now that means that this would actually be another one that I could get away with just tacking a 1/4 onto my antiderivative of a square root. But we're practicing U-sub, so that's what I'm going to stick with right now. So when I rewrite this integral, this is now an integral of the square root. This 4x minus 1 is now a u. And then in place of this dx, I'm putting in the 1/4 du. That 1/4 is a constant multiple, so I'm going to pull it out in front of my integral. And then I am going to rewrite this square root of u as u to the 1/2 power, because I think that'll be easier to do an antiderivative of. So that's phase 2, right? I rewrote my integral. Phase 3 is let's go ahead and take that antiderivative. So my antiderivative would be, let's see, 1/4. Add 1 to my exponent, so this would become u to the 3/2. And then down here, I'm either going to divide by that 3/2 or multiply by a reciprocal, so this is going to be a 2/3. My work's all blending together here. Sorry about this. And so then my final answer, when I swap the u back out for the 4x minus 1, I'm also going to go ahead and put together the 1/4 times the 2/3. So that's 2/12, otherwise known as 1/6. In place of u, I'm going to stick that 4x minus 1. And that's to the power of 3/2 plus c. And that's my antiderivative. But again, really, this is just, here's the antiderivative of a square root, right? That's what the antiderivative of a square root would look like, times the 1/4 that came from the derivative of 4. So anytime your inside function has a derivative that's just a number, you can just kind of make that leap. You know that all that's going to happen is that 1/4 is going to end up outside your antiderivative. So again, hoping that you won't have to use U-substitution every time. Let me model that for you with this next one, okay? Because this is another one that could be an easy one. The 7x plus 5, if I were to find the derivative of it, it's just a 1/7. I'm sorry, it's just a 7. And that means a 1/7 is going to show up in my antiderivative. So I could just jump straight to an answer here by saying, I know it's going to have a 1/7 times antiderivative of cosine is sine, and then the 7x plus 5 stays in place, plus c. If you want to try U-substitution and see where that comes from, that'd be a great idea. That would be a great way to practice. But with those ones where the derivative is just a number, this shortcut will always work. All right, let's get to some where you can't take a shortcut, these last 3 down here. So, again, what you're looking for u is always the inside function. You're looking for a function that's inside something else. That almost always will, stand out to you. You'll almost always be able to identify it that way. So let's take this 3 minus 2x squared, because that's inside a cosine squared, and call that my u. So u is 3 minus 2x squared, which means du. 3 goes away, so that's going to be a negative 4x dx. I'm going to swing that to the other side. I know it's tempting to add it, but these are connected with multiplication, so I need to divide. This step is almost always going to be a 1 over something, and I want to make sure I write this correctly. It should be a 1 over negative 4x du equals dx. Now, if this is weirding you out a little because there's x's and u's involved, good. Okay, that is weird. We don't like that. But we're going to fix it in just a minute, and you'll see kind of the true purpose of what U-substitution is designed to do. Okay, so if I rewrite this thing, I still have this 4x. That's a problem, and we'll talk about that in a second. The bottom is now a cosine squared, but that part that's circled I'm going to replace with a u. So I have x's and u's in the same problem, and that does not fly. That does not work very well. But I'm also going to take out this dx and replace it with this down here. So then I have a 1 over negative 4x du. We want to keep the u's. We want to get rid of the x's. Okay? And what I want you to notice is that I have a 4x on the bottom and a 4x on the top. That is good news, right? That is the purpose of U-substitution, is to make this x go away. I do still have a negative here. Let's not lose track of that. So when I rewrite this again, I'm going to put a negative outside that integral. And then one more thing in this problem that makes you know, the next step possible. I'm seeing a 1 over cosine squared. 1 over cosine squared is really the same thing as secant squared. And if you can think about it that way, that'll make the antiderivative much easier. Okay, so that was us simplifying this integral, right? We took this integral, we did some U-substitution, that brought us to this, and this is something I can actually take an antiderivative of. That's your goal, right? So the antiderivative of secant squared is tangent, right? Because secant squared is derivative of tangent. I need to keep that negative. So I'm going to say negative tangent of u. And then let's go back and put our u back in. So my final answer here would be negative tangent of 3 minus 2x squared plus c. Okay. The next two, when we did them in class, I had students try them on their own, and I walked around and checked on them. So I would strongly encourage you. I'll get you started on the next one with helping you pick out what you should be, but I would really encourage you to pause the video and try these, and then come back and check and see if you got them right. Okay. The one thing that is helpful to understand about this is when you see this sine to the fourth of x. This is really the same, and let's see, I don't have a ton of space on my paper. Sine to the fourth of x is the same as sine x to the fourth power. So if you understand that, that helps you figure out what u should be, right? U is equal to sine x. And right now, because I've done a million of these problems, I can kind of look ahead at what's about to happen and understand why sine x is a good choice, because ultimately I'm going to need to get rid of this cosine x. Okay, I can deal with this with U-substitution, but I need to get this out of the way. So what's the derivative of sine x? Well, that's cosine x. This does get a little bit tricky because you're kind of mixing derivatives and antiderivatives, so just make sure to keep that straight. Let's divide by cosine x, and we end up with 1 over cosine x du equals dx. And again, you should be thinking ahead to like, okay, if that goes up in place of dx, is it going to do something helpful? Well, yeah, it's going to cancel with that cosine, right? So when I rewrite this integral, this thing, remember, is really this. And that sine of x is now my u. So I can rewrite that whole expression as u to the fourth times cosine x times this thing, 1 over cosine x du. And we don't like the x's and u's mixed together, but it's okay because these x's are about to go away. And I don't really care about that 1, right? That's not going to change anything. So I really just have an integral of u to the fourth. That's an antiderivative of u to the fourth. Antiderivative would be 1/5 u to the fifth. And then let's plug our u back in. So 1/5 sine x, because that's u, to the fifth plus c. Okay, one more example for this lesson, and I'll leave you be. Let's think about what u should be here. What would be the most helpful thing for you? Sorry, I gotta move my camera around a little bit here to get to the bottom of that page. We are looking for a function inside another function, okay? And so what I'm seeing here is a negative x squared inside the e to the something function. Right? That's a negative x squared that's been put into that exponent spot. So that's what I'm choosing as u. By the way, again, just a reminder, I encourage you to pause the video and try this on your own. Du would be negative 2x dx. Swing that negative 2x to the other side, and you have 1 over negative 2x. Du equals dx. Let's rewrite our integral. Do not skip this step. The integral, the x is still there, right? Nothing's happened to it. The e to the negative x squared, that negative x squared that's circled, that's what I'm replacing with u. So this becomes e to the u. I like this. I can do an antiderivative of e to the u, but I can't do it until x is out of the way. But let's replace that dx, right? Dx is 1 over negative 2x times du. And what I see here is an x on the bottom of a fraction with an x up on the top of the fraction, right? And so this x and this x cancel. I do still have a negative 1/2. That's a constant multiple. So I can say negative 1/2 integral of e to the u. And now this thing that we've done all this conversion with, this is something I can actually do an integral of. That's the point of U-substitution, is to get you to a place where you can do an integral. So I know that that negative 1/2 gets to just come along for the ride. Antiderivative of e to the u is just e to the u. And then let's place that u back in. So negative 1/2 e to the negative x squared plus c. So our goal today is to try some of these. This is usually a lesson that we spend a couple of days on because it takes a little while to get good at these and build that instinct, you know, especially for picking out what u should be. But sometimes you have to just try something. Sometimes you have to just pick something and run with it and see what happens. So go ahead and give the homework a try for these. And then tomorrow's lesson, we will take a look at, we're going to add kind of one more tiny step onto this, but we're mostly just practicing this process some more. So have a great night. We'll see you soon.